Hello, so today I'd like to talk about partial differential equations for scientists and engineers by Stanley J. Farlow. It's a very catchy title, probably not one that is used on 50 other books. I like this PDE book a lot. So it's got, the obvious advantage that it's Dover, and at least when I picked it up it was $16, which certainly beats $150 or $250. It also has the advantage of being very well laid out. So if you come to one of these lessons, like the Fourier transforms here, you see it has a nice purpose of the lesson, a short introduction to it, and then it will have one example, right? So got an example here, and then the solution of an initial value problem, and so on. So we have all this going on. You can see I definitely use this book. So I think this is a very well laid out book, and I think it does a very good job of going over partial differential equations. A little bit might be dated at the very, very end, but for the most part it's very good. It goes basically, let's say, lecture by lecture through a year's worth of partial differential equations, right? I think the thing I should say here is that I didn't have a partial differential equations class in college. I had, a mathematical methods for physics class. I had a electrodynamics class, electricity and magnetism class. I even had a computational methods class, but I didn't have a PDE class itself. So, although I was familiar with a lot of these things, I hadn't had sort of a coherent introduction to partial differential equations. Instead, I had, bits and pieces of it here and there, which is fairly normal for a physicist. It was common at my school for most physicists to get a math minor. I think this is probably common in a lot of places, since you already have to take through differential equations and linear algebra. You usually have most of that math minor done, and I think really to get a math minor you only had to take the PDE class to get it. I'm not exactly sure. It's also common for people to have a dual major, and I did as well. But I took a lot of classes like abstract algebra and advanced calculus and things like that. So I took what they called a pure math major or a theoretical math major. One of the two, I'm not sure which. And so I never got a PDE class in. A couple of years ago, I did decide to go through a PDE book. And since I had this book already available, I already picked it up because it was cheap and it was something I could use as a reference if I needed it. It's a pretty good thing to have around. I use this one. And I had always been impressed with the way the layout looked. I just hadn't gotten through any of these particular lessons, which I probably should have done previously, but I just hadn't until I got here. So, like I said, this is fairly well laid out, and it's got each one of these lessons here basically is for one class. You see there are 47 lessons. That's approximately 2 semesters worth of hour and a half lectures, or 75-minute lectures, really. But, and so that's what I think this is. I probably is, because I probably read the introduction as well, but that's been a long time. And it goes through, and it just goes through the 3 different types of problems, right? Diffusion, hyperbolic, and elliptical types of problems, as well as going through numerical or approximate methods. And I think basically you get through here, that's probably the first, I'd say if it was this, the first semester would get you to somewhere around here, the vibrating beam. So, I mean, it is possible this is one semester. That's still a little bit much for one semester, but not too much. Not too much. 14 times 3 is 42. So probably, including all that other stuff, it's probably just one. It's probably 2 semesters. So anyways, starts off with talking about partial differential equations. And then he goes through 14 lectures on diffusion problems, just what they are, parabolic equations, right? Boundary conditions, and he talks a lot about boundary conditions. Does he talk about them in lesson 1 or lesson 3? So he does talk about, no, lesson 1 is just categorization, which is common. Somewhere in here he talks about the difference between boundary and initial conditions, but it looks like I'm not going to find them just flipping around. Initial conditions, boundary conditions. Basically, boundary conditions are places in space where you have some condition, and initial conditions are places in time. For diffusion type problems and hyperbolic type problems, they're fairly simple. We'll get to more complicated ones with the elliptic type problems. And so, we go through here and we do different things. The derivation of the heat equation, that's interesting. These are all very important problems. Each one of these types of differential equation, partial differential equation, shows up everywhere in the physics. The separation of variables. Separation of variables is very important. Hopefully you've seen that before. That's the easiest way, if you can do it, to start solving your partial differential equations. And in fact, most of the methods for solving partial differential equations are sneaky ways to turn them into separations of variables, or to, like the Fourier transform, to just decide that they're not find a way to turn them into algebraic equations, and then you don't have to do any really interesting work on them. Separation of variables, that's the most important one. That's basically getting the equation in such a state that on each side you only have one kind of dependence. If you can do that, you're home free. So a lot of transformations are going to try to get you into this. Then you're transforming non-homogeneous boundary conditions into homogeneous ones so that you can solve them. Solving more complicated problems by separation of variables. Transforming heat equations into easier ones. You notice how this is working out? Everything's trying to make the problem into an easier problem. That's basically math right there. That's what mathematicians do. Solving non-homogeneous PDEs, eigenfunction expansions. Integral transforms like the sine and cosine transforms and the Fourier series and the transform and the Fourier transform and applications to PDEs, the Laplace transform. All of these, Fourier and Laplace transforms, all those things are just trying to change the system into one that you can solve algebraically, right? Whether you're doing it just depends on how you're going to do it. It's really an integral transform. They're integral transform methods, right? That's what it says right there. And you go from one basis to another, basically, and you're saying, okay, what I'm basically going to do is I'm going to turn ddt into I omega, or something like that. That's more or less what happens. It's a little more complicated, but sometimes that's all that happens. I remember in graduate school going through a bunch of papers and being just amazed, right? After seeing, integral transforms as integral transforms in my math methods classes, in my electrodynamic classes, going off and seeing what people actually do in practice, which is just say, okay, well, I'm going to take this derivative and I'm going to put I omega in instead of. And unless you have something complicated, for most things, that just works. And now all of a sudden you have a really easy problem to solve. Similar things happen with Laplace transforms. Lesson 15 here adds one extra term into the diffusion problem, the u sub x. This u sub x here, that's not a component, that's a derivative. So this is du dx. So that's one thing that you have to learn. And if you're going through one of these things, you will learn that. I won't sit here and try to teach you differential equations by reading the contents of a differential equations book. Hyperbolic type problems, you get into a wave equation, very important. The D'Alembert solution to the wave equation, more of the same. Boundary conditions with the wave equation, the finite vibrating strings, things that we all really care about. These were very important. Actually, I didn't get enough of vibrations like that when I was in college, so these were actually very good. I liked having these vibration problems because I knew their importance, but I'd never really taken the time to do a whole bunch of them because you only have so much time in college, right? And they weren't the things that people were really interested in getting me to learn in my classes. And then you go in dimensionless problems. Very important to be able to put things into a dimensionless form. So this is a very important thing to do. I will not. I want to go look at it right now because I don't remember it very well. Then you have a bunch of different systems. Superposition. This is very important. This is a thing that happens in linear systems. This is what you do with wave equations and stuff like that. Is as long as you have no nonlinearities, you can just add up solutions, right? And you add up the different possible solutions, different simple solutions, let's say, eigenfunctions, and different linear combinations of those will work. And if you get the linear combination that matches the boundary conditions and the initial condition and so on, then you have a solution. You have the solution, actually. This is a nice thing about linear differential equations. If you get a solution, you have the solution. That's nice. Assuming you have enough boundary conditions to actually solve it. First order equations, turning things into first order equations. Nonlinear first order equations make things hard. Systems of PDEs make things really hard. And this is basically what I had to worry about for the analyses that I did in graduate school, is systems of PDEs. And I guess similarly for the work I did at NIST. The vibrating drumhead, wave equation in polar coordinates, and you've seen that a little bit in your freshman physics textbook, right? So if I come down here, it's always so tempting to do this, and I shouldn't do it. If you come down here, you'll see he's got all these patterns that are the vibrational modes here. The one in your freshman physics textbook, the one that costs $400, that's a much better illustration. It's probably not worth the $400 difference in price, but it's a much better illustration, and you probably already had to buy it. Elliptic type problems, and he's starting to talk about the Dirichlet problem. Here, where is it? Oh, there it is, general nature of boundary value problems. He goes through and he actually characterizes, I don't recall him doing this earlier, the different kinds, the fixed and the fluxed conditions. The Dirichlet conditions, which are the fixed conditions, which are at the boundary of my surface, let's say I've got a circle or a sphere or something like that, depending on the dimensionality, I say this is going to be the value at that surface. And then I sort of do what I can to find the solution with that value. Then there's the von Neumann boundary conditions, the flux conditions. And there I'm fixing how much is coming in or coming out, or basically of the thing. I'm fixing the first derivative of those problems. And there's a third one in there that I can't remember, which is just mixed. So the third one is the Robin boundary conditions, which are just mixed boundary conditions. And there's a section on spherical harmonics. It's one thing that'll drive you crazy. And there's another one on Green's functions. You'll get a lot more spherical harmonics in, let's say, your atomic and molecular physics text, or in a graduate electrodynamics text. You'll get a lot of those, but here you don't get very many, and you don't really get the Green's functions either. That's another thing that you'll have to wait for. That is probably more fit. I don't know how much mathematicians use the Green's functions. I know physicists do a lot. Engineers have a different name for it. It's called the impulse functions, but they're basically the same thing, which is you solve the PDE for a impulse for a delta function, and which is a infinitely thin function that has a value of 1, has an area of 1, so it's a kind of weird function. If you don't know what a delta function is, that's the Dirac delta function. So solve for the Dirac delta function, and then you can build up any of your other solutions based on the solution to that impulse. And then you have the numerical and approximate methods. There are fewer, I guess there are fewer things here when I went through it than I thought. So there are the finite difference methods, which are basically turning all of your differential equations into difference equations on a grid, and then solving for that grid. This is what you're going to do on a computer. So this is a very old book. Does this tell me right away? No, it's 1982. So it's still fairly old. So if you'd gotten the original edition in 1982, you could have done some really groundbreaking work on your Apple II Plus, implementing some of these. A discussion of analytic versus numerical solutions, that's nice. But more classifications of PDEs. Monte Carlo methods, we just had a talk about a book that uses all Monte Carlo methods in statistical mechanics. That's another important one. That's basically, like I said in that other book. I should not draw in my books, other than nobody's ever going to buy this one anyway. You already seen sort of the state it's in. But let's say I had a circle inside of a square. A Monte Carlo method would, to figure out the value of pi, would be to randomly place dots all over here. And I could find pi by comparing the area or the number in the circle over the number in the square. Number in the circle should have, let's say, pi r squared. If this is r, and this is 2r. So this should have pi r squared, and this should have 4r squared. So this ratio is approximately equal to pi over 4. Right, and that's the simplest sort of example for Monte Carlo method. This is very slow, and there are ways to speed that up. And actually, the same is true for all numerical methods. Numerical methods are slow, and then you try to speed them up. There are ways to take, especially like these finite difference methods, and speed them up by plotting, right? If you say I've got a grid of size 1, and then let's put this as 1, and then I have that, and then I have a grid that size, and then I have a grid this size, then I'll have a solution for each one of those, and we will have a extrapolation, and it's a dude's name, to 0 here, and this is going to be the actual this is going to be the actual solution, and this converges. So that's something that's important. And you say, well, I can't see why this would be important for this. Well, this is the first thing in my numerical electromagnetics class that we did, so it's still important for those sorts of solutions. Then we have variational methods for PDEs. This is the method of Ritz, he calls it. This is basically the Euler-Lagrange equations that I talked about last time. Perturbation methods, also very important, and conformal mapping solutions. And now I'm feeling really guilty. I'll remember to erase it sometime. So those are the lessons in here. There's no 48th lesson. That is something with physics books that always sort of annoyed me. You know, you might have an introduction like this. If you don't have for lesson 1, but you don't have a lesson 48. That lesson 48 being the conclusion, right? So what bring it all together. What did we just learn in this class? So that tends to be a problem. So what I think was an interesting one. Let's just go to 253. Oh, well, no, this is a good one here. So I just wanted to go through one of these lessons and show you what it looked like, right? So one of the things I like here is there's a short purpose to the lesson. I try to do these in my notes for class, and they end up being, a page and a half long before I start talking. You can tell I talk too much, and same thing in my lecture notes. Then you'll see that he's got sort of a basic idea about what it is, right? What are we trying to do here, right? And he's got, the basic idea of superposition there. And you'll notice he says IBVP. That's an initial boundary value problem, which means you have an initial condition and you have boundary conditions and you have your PDE. So in this book, he always sets these up like this. He sets up every problem with, well, what are the partial differential equations I'm trying to solve? What are the boundary conditions? And what are the initial conditions? All right. These are the things that physics gives you, right? So the work that's for the physicist is to get to this point, right? And then he solves them because, he's got these methods. Or if it's really hard, then he goes to a mathematician, asks the mathematician to solve them. But usually now that really is just, the computer. But the idea is that for the physicist, all of his techniques are really designed to get him to this point where you've analyzed the system so that you know what the governing equations are and what the boundary conditions and initial conditions are. For the mathematician, that's where we start, right? And we say, okay, now that we know what these things are, we want to go ahead and find a solution. So this is how you find a solution for that. So now, after talking about what the kind of problem is, now he says, well, what kind of solutions do we have? And you see what he's doing is he's trying to take this and put it into a number of smaller solutions, right? These A sub n, B sub n, F sub n sort of things. And if you have these smaller solutions, then you can later on add them back together. And that's basically for the superpositions. And then you'll usually have a note or two here. Problems. So the problems are fairly direct. Some of them, right, these are just, these are really simple here. This is solve a thing. Usually there'll be a complication added to the example in the text. And I don't remember this one. This is taking an ordinary differential equation and doing the same thing. because I mean the point is to work on these different things here, work on these different solutions, work on these different, not solutions, but methods, right? So this is just a big methods book, which is why it made a good reference text, right? That's why I wanted a reference text that's one, cheap, and two, thin, right? I don't think I have, I don't have any textbooks in range, but this I can carry around with me, right? I would not carry your normal PDE book with me either. So, like I said, a few years ago, I went ahead and worked through all the problems in this book. Well, I worked all the problems in this book. Not all of them were correct, but I did go through the book and tried to work through all the problems. There aren't a lot, so it's a good book for going through. Like I said, 6 problems per chapter. Now, that's probably for somebody who's taking 4 or 5 classes. 6 problems per chapter ends up being about 12 problems per week. So that's a lot of work, right? But that's more or less what you do in college, right? So, I mean, it does take some time. It took me a little more than a summer, so I had to do a little bit of extra work during the semester to finish this up, but I got through more than half. Do I want to? I think I was sitting here in the 30s when I was done, and then doing finite difference methods and Monte Carlo methods wasn't a big deal, especially since, like I said, I'd already worked that other problem, and I've done a lot of things with finite difference methods in the past already. That didn't end up being much of a problem. But going through the analytical solutions was a little more difficult for me because, I hadn't done quite as many. I hadn't done as many PDEs as I did in this book, at least since I did Jackson. Right, Jackson that's classical electrodynamics. I may have done more PDEs than that. I'm not sure. But a lot of those use really, really cool methods that are possible with electrodynamics, like the method of images. And I have to stop thinking about the method of images because I love inventing problems with the method of images. Anyways, Partial Differential Equations for Scientists and Engineers by Stanley Farlow. If you want to learn partial differential equations, this, I think, is an excellent text, and it's cheap. All right, it's a Dover book, so it's cheap. I don't know how much it costs now because I've had this forever, as you can see. Even with the contact paper on it, it's looking pretty ratty, and seen at least 1 cup of coffee. So, all right, so that is my favorite PTE book. Thank you very much for listening. Bye now.